Okay, so welcome to Lecture 6 of Introduction to Quantum Computation for the Summer 2020 offering at the University of Paderborn. So today's topic is going to be entropy and entanglement distillation. Okay, so in terms of high level, this is basically a hardcore quantum information lecture, basically. Next week, we'll start talking about algorithms. Okay. So I'm going to start by reading the quote at the top of this lecture, right, which is by Aristotle, actually. So this is probably the oldest quote we'll have in this course. And here he's writing about the process of distillation. And he writes, seawater is rendered potable by evaporation. Wine and other liquids can be submitted to the same process, for after having been converted into vapors, they can be condensed back into liquids. Okay? So why am I writing down this quote? Well, the basic idea in this lecture is going to be, so far we've talked about things like entanglement in quantum systems, right? And we've come up with criteria for, okay, when is a quantum state entangled or not? But we can actually do something a bit more fine-grained than that, right? I mean, in certain settings, we can actually quantify in some unique and rigorous sense how much entanglement is in a given quantum state, okay? And once we know how much is in the entanglement is in a quantum state, as we saw earlier, for example, for things like the Teleportation Protocol, there we really needed a maximally entangled state. I mean, we didn't know it was maximally entangled at the time, these Bell states. Today, of course, we'll get the tools to argue that indeed the Bell state is maximally entangled. So, but given a state that's not maximally entangled, can you kind of boost it somehow to something that is maximally entangled so that you can use it for something like teleportation? Okay. And that's this process of distillation, okay? Given the so-called noisy entanglement, can you kind of clean it up? Can you distill it into, pure state entanglement? Okay, good. So those are the two kind of questions we want to address in this lecture. How do we quantify the amount of entanglement in a state? And how do we increase the amount of entanglement given many copies of the state? And to do this, the main tool we're going to use is entropy, okay? So some of you may or may not have heard of entropy before. Entropy itself is, one of the most influential mathematical ideas from the 20th century. You can write entire books about this, okay? And more or less, if you pick up a quantum information textbook, like, 2/3 of the material will have the words entropy in it, okay? It's incredibly important and central. And so, of course, we're going to spend some time in this lecture talking about entropy. That's the first thing we're going to introduce. Okay, so let's do that. Okay, so entropy. So this is section 1 in the notes. Okay, so entropy was introduced in 1948 by this paper of Claude Shannon. And essentially, it founded the field of information theory as we know it. Okay? And the goal of information theory is to study a very natural question, which is, how well can you transmit data? And that, of course, is going to involve compression of data, right? Because you don't want to necessarily transmit all the bits. You ideally want to compress the data so that you transmit as few bits as possible, okay? And for this, it turns out that the right notion to quantify this type of, or to study this type of data transmission is the entropy, okay? And of course, what we're going to do is we're going to first study the classical notion of entropy, so in classical data sources, and then we'll generalize it to quantum entropy in terms of the von Neumann entropy, okay? So the classical entropy to distinguish is called the Shannon entropy. Typically, we think of the quantum entropy as the von Neumann entropy, okay? So let me begin with the Shannon entropy, which is the classical entropy. Okay, and so again, this is one of those things that, even if you never take another quantum course, knowing about the entropy is a very, very good thing to have under your belt. Okay, no matter what you end up doing in computer science moving forward. Okay, so roughly speaking, the Shannon entropy is supposed to, given a random variable, it's supposed to quantify in some rigorous sense what is the amount of uncertainty or information hiding in that variable, for example. Okay, so let me first formalize the setup. So let's suppose we have a random variable. Let x be a discrete random variable. Okay. And, it takes values from the set, let's just call these values x1 up to the sum xn. And, for brevity, I'll just write, the probability of xi. That just means that, of course, what is the probability that my random variable, capital X, takes on, or the value little xi from the set. Okay. So what I'm going to do now is I'm just going to write down the definition for the Shannon entropy, and then we'll digest it and actually rederive it to see where it comes from. Because when you first stare at this, it's going to make at least no intuitive sense. So the Shannon entropy, how do we define it? We use h of x, so x is the random variable as input here, right? H is just the notation, and we define it like this. It's going to be a sum. And you'll notice how I have n terms in the sum. That's because there are n events, right, in my space over here. There are n possible events, so I'm going to sum over all of them. Okay, and a probability of each event should somehow be incorporated into this expression, right? Because I'm trying to understand how the random is this random variables distribution, right? And what makes it look a bit funny is I'm going to put a minus here, and then I'm going to put a log here. Okay, so this is one of the most important expressions you will see in your technical careers, right? This notion of entropy. Okay. Let me be clear here that the log here is taken base 2. So in general in this course, logs are base 2 unless otherwise specified. That's standard for CS courses. And there's one other thing, again, when you first see an expression, especially a funny looking one, you should think about the base cases, right? So what is a base case here? Well, or a boundary case, I should say, not a boundary case. And that's when you really understand something, right? When you understand the boundary cases. Well, this can take on any value between 0 and 1, and that's fine, right? But the log function, if you give it something, what does a log function look like, right? It looks like this, right? Here's your log function. It's some monotonically increasing function like this. This is log of x, right? And, well, in particular, you'll notice that it's not defined at 0, right? There's this vertical asymptote. So what happens if over here, I plug in a probability of 0, right? Then the log function is technically not defined. But of course, we're also lucky because when you plug in 0 there, that's the same term in front, right? Then this would also be 0. So what we're going to do is we're going to make a notational convention that 0 times the log of 0, even though it's technically 0 times minus infinity, we're going to interpret that as just 0. Okay, so this is important for this to make sense. Okay, so that's just the definition of the entropy, and I'll let you stare at that for a second. Okay. Now, I can define technical terms till the cows come home, or formulas, but the question is, what is the motivation of this thing? So before we even talk about where it comes from, motivation. Before we even talk about where it comes from, let's talk about the motivation, okay? And then we'll derive the expression. Okay, so this is based on, the formula is based on data compression, right? So suppose you have, you're in Germany, let's say, and your buddy's in Canada, and you want to send them some message, right? And obviously you don't want to send all the bits in the message in general. If you can get away with compressing it to a smaller number of bits you have to send, then that's obviously what you want to do, right? It's much cheaper to do it that way, okay? Now, of course, a compression scheme is completely useless unless you could decompress at the receiving end, right, and recover the original message, right? I mean, here's a silly compression scheme. Whatever string you give me, I'm going to send it to the single bit 0, right? That works incredibly well, right? Wow, I just need to transmit 1 bit 0. But of course, you cannot recover the message at the receiving end, so it's useless as a compression scheme. Okay? And the point here is that, Shannon's noiseless coding theorem basically says that the minimum number of bits you need to transmit kind of on average in order to be able to decompress and get the information back at the receiving end, roughly speaking, that is the entropy. Okay, so that function turns out to be the right one to think about if you want to think about compression. Okay, so in a little bit more detail, but this is still a rough statement, the noiseless coding theorem says that in order to reliably transmit n IID, meaning independently and identically distributed random variables xi from some random source x, it is necessary and sufficient to instead send the entropy number of bits of communication. Okay, so let me just briefly write that down. Shannon's noiseless. Okay, so here you're assuming you have a perfect transmission channel, coding theorem. Okay, and this is very roughly. This is not a formal statement. So it states that to reliably transmit n IID. Okay, and remember this means henceforth in this course identically and independently. Independent. All right, let's just fix it properly. Independently. Random variables. So random variables RVs are random variables. Another shortcut I'll use in this course. Okay, x I from a random source x. Okay, it turns out to be both necessary and sufficient to send the entropy of your source bits of communication. Okay, this is all in the classical world. Again, let's just be clear. This is all classical communication. And let me really clarify, stress that you both need this much amount of communication, right? So you can't do with anything less, really. And it's also sufficient. You actually can do compression up to that threshold, basically. That's what Shannon's noiseless coding theorem says, okay? So I'm not going to get into details into the formal statements and what exactly this means beyond that. This is just a hand-wavy statement to give you a sense of, why do we care about the entropy? Where does it actually come up extremely naturally? Okay. Now we are going to play with this expression, right? We're going to evaluate it. So I do want to take a moment to actually derive the expression. Like, where does it actually come from, right? Because it looks a bit like voodoo magic right now, right? So let's derive this expression. Okay, so the heading I put in the notes is, getting our hands dirty, because now we're actually going to see where this comes from. No more waving hands. Okay, and so, let's understand by first looking at special cases, right? So whenever you want to formalize something, you always start by thinking about special cases. And then you kind of see, based on the special cases, what kind of function do we want to define that will capture, in a way that we like, the notion of how uncertain is a random variable. Okay, how much uncertainty is there in it? Okay. Okay, so let's consider two boundary cases. Consider two cases. Okay. So the first case is number one, a fair coin flip. Okay, so if I were to take a coin, heads or tails, right, and flip it, so my random variable x takes values in the set, let's say heads and tails. Maybe I shouldn't call it h because that's conflicting with the notation for entropy, right? Shannon entropy. So it takes values in heads and tails, right? And with probability WP, a half each. Okay, so I have a fair coin flip. What is the entropy of a fair coin? Okay, and here we're just going to plug in the definition, right? So let me just go back up. So what is the entropy of this thing, right? Well, it's going to be, I have two events, right? So I have two terms in my sum. So it's minus the probability of the first event, which is, say, heads. So the probability of, okay, sorry, let me do it explicitly the very first time just to be very clear. So minus the probability of heads, right, times the log base 2 of the probability of heads minus the probability of tails, okay, times the log base 2 of the probability of tails. Okay, so that's the entropy of x, and now we could just plug in our expressions that we have. So the probability of heads, it's a fair coin, so it's a half, and so I also have a log of a half here. And minus a half times the log of a half, again, because probability of heads equals probability of tails. Okay, and now what is this expression? Probably the easiest way of doing this, and also to see where the minus signs come from, is just remember that the log of 1 over x equals to minus the log of x. right? So the log has this nice property that if you raise the argument to the log to some power, so here, for example, this x to the -1, this thing over here, that's the same thing as bringing the exponent out in front. Okay. So what does this mean? This means that this is just going to be a half of log 2 plus a half of log 2. Okay, so I lose the minus sign, but I also flip what's inside the log. And so what is this? Remember, log is the power to which I have to raise the base in order to get the argument. So the power to which I need to raise 2 to get 2 is just 1. And so, of course, here I get a total of 1. Okay, so it becomes a half plus a half. So this tells us that a fair coin represents, on average, 1 bit of information. Okay, so in other words, if I want to think back to this information transmission setting, if on average I want to transmit the answer of a coin flip from Alice to Bob, from Germany to Canada, let's say, I would have to transmit a 1 bit of information, right? And intuitively, this makes complete sense because if Bob is waiting in Canada for the coin flip answer, because it's completely random, right? If I send anything less than 1 bit of information, there's no way he's going to guess the answer of the coin flip basically with anything close to probability 1, right? I mean, so for example, if I don't send a bit at all, the best he can do on his end is just guess the answer. And that has probably a half of succeeding. Okay, so it sort of makes sense that, the answer should be 1 here for the entropy. Okay, so that's one boundary case where you have something that's really completely unbiased random coin flip. Now we can do the opposite extreme, which is what happens if you have an extremely biased coin flip, right? So here we have a very biased coin flip. So by that I mean that the probability of heads is going to be, say, 1, right? And therefore the probability of tails is 0. Okay, and so what is the entropy of this source? Okay, I'm just going to plug in the values into this expression up here, right? So the probability of heads is now 1, so I have -1, and then I have times the log of 1, right? Minus the probability of tails we said was 0 times the log of 0. Okay, and here remember that I was careful to define this as being 0, right? Even though log of 0 is minus infinity, technically speaking, the product will define as 0. And so therefore what I get here is what? -1 times, and so what is the log of 1? The log of 1 is, sorry, I'm doing something wrong here. I should get a 1 out of this, right? Sorry, I should get a 0 out of, oh, sorry, of course. So the log of 1, what is that? To what power do we have to raise 2 to get 1? Well, 0. Right, so this is 0, and then you get 0. Good. Okay. So the entropy for a completely biased coin flip is 0, and this makes a lot of sense, right? If Alice is flipping a coin that both Alice and Bob know is extremely biased in this way, then Alice doesn't have to transmit any information across the channel to Bob in order for Bob to know the answer to the coin flip, right? He always knows the answer is heads, period. Okay. Good. So in this case, there's no uncertainty. Okay, and so that's kind of the intuition as to why the entropy sort of makes sense. Let's kind of derive it now. Okay, and so the key idea, kind of dating back to Shannon here, is that the less likely an event is to occur in your distribution, in some sense, the more information it conveys. Okay, because let's see, so the less likely an event is to occur, the more, in quotes, of course, information it conveys. Okay. So this is the idea. And so what you want to do is you want to say, okay, look, fix your favorite event. Doesn't matter which one right now. And now I want to specify, okay, how much information is encapsulated by this event? Like when xi occurs, when my random variable takes on value xi, how much information does that convey? Okay. And so let's define this notion of information content. Okay, information content. Of xi, we'll define it as I of xi. Okay. And the formula we'll use is the log of 1 over the probability of xi. Okay? And now I could move the minus sign outside and get rid of the fraction, which I will do. The log of the probability of xi, right? Okay. So that is how I'm going to define the information content of xi. Okay. So notice how, so let's just understand why we might want to do this, right? Why did I put this funny log function, and why do I have 1 over the probability, right? So first, let me just make some observations. So observations, number 1. So as we saw, the log is monotonically, so log of x is monotonically increasing. Okay, so in other words, if x is greater than y, then the information content of x is strictly larger than the information content of y. Okay, these are just for the arguments, x and y. Okay, and this is of course for any x and y in the open interval 0 to infinity. Okay, so what does this mean basically? This means that, how do I get a bigger argument? Well, the smaller the probability here is in the denominator, right? The more this term blows up, right? The reciprocal blows up. And therefore, rare terms will have a larger argument to plug into the log. Okay, so their information content will be larger. So the log function in this sense satisfies what we need, right? Which is that rare events give me a larger value for the information content function. Okay? Okay, now, why did I use log, of course, right? I could have just forgotten the log and just looked at the reciprocal, right? And certainly then 1 over probability would still have had this behavior that, smaller probabilities give me a larger function value. Okay, but there's a reason why the log is very helpful. Let's look at some other properties of this function, and we'll get to that in a second. Okay, so here's another observation. And this is basically that the information content is non-negative, obviously, right? In order for it to be meaningful. Okay, so, and that just follows because, the log function is going to be, well, okay, our values here, the probabilities are between 0 and 1. So that means that, this function, the log function, at that, because we're doing 1 over this, right? The log function in that interval between 0 and 1 will always be non-negative. Okay. And number 3 in this list, I guess, if an event occurs with certainty, the occurrence conveys no information, right? If an event occurs with certainty, conveys no information. Okay, so in other words, if the probability of x is equal to 1, then I should say the information content of, technically 1 over x, right, is, if the probability of x is equal to 1, then I should say that, the log of 1 over the probability of x, right, is equal to 1. Okay, so I guess, I'm going to abuse notation and say this is the information content of x, basically. Oh, I guess I did define it that way. Okay, good. Okay, so the information content then, sorry, this should be 0, sorry. Good. It's confused there, right? So you have 0 information content, not 1 information content. Okay, good. And now the third property is, now we're really going to use the log function. Why did we like that log function, right? Okay, because otherwise I could have picked any other monotonically increasing function, right? So I could have done, 1 over probability of x, and instead of putting a log here, I could have put some other function, right? And maybe still been able to satisfy, this 2 and 3, right? Which are kind of some basic properties I'd like to have. Okay, but the reason why the log is so nice is because of this thing, right? It deals very nicely with independence. Okay, so let me remind you that, recall that if I have 2 random variables, x and y, we say that they're independent, okay, if the probability of that x equals to some value little x and y equals to some value little y That just is the product of the probabilities. Okay, so these things are really uncorrelated, these random variables. Okay, so that was just the classical definition of random variables that are independent. And the key point here is that, if I have two random variables and they're independent, then somehow the information content from these two sources, right, because they have nothing to do with one another, the joint information content together should be the sum of the individual information contents, right? I mean, there are no correlations between the two. So we would expect, right, if we define, right, the event, let's say z, to be the event that both x equals to little x and y equals to little y, then we would expect intuitively that the information content of this joint event, right, should be additive. It should be the independent, the information content of each of the events x and y independently, because they have nothing to do with one another, right? Okay, and the point is that due to the log function, we get exactly this property. Okay, so the log function guarantees this. Okay, so it basically guarantees that, if I have a joint event, then the information content becomes additive. Okay, so, why is this true? So I'll let you do this on your own, but just very briefly. So which property of the log is it that guarantees this, right? So remember here that if I have the log of a times b of two scalars, right? What it does is it converts it very nicely into a sum. Okay? And that's exactly how this property follows, right? I mean, intuitively, I'll let you work out the details on your own, but here, if you're independent, right, then you're a product of probabilities, and guess what? The log takes a product to a sum, right? That's how these things fit together. Okay? So for a single event, just to recap, xi, the information content is going to be 1 over the probability, and we stick a log function on to make sure that independent events, their information content is additive. Okay? Now this is just for one event, right? So this was for a single event. So now we can define Shannon entropy. Okay, this is for one event. So for one event, I defined it as the log of 1 over the probability of xi, right? And now, of course, my random variable can take on multiple events, not just one. So what I want is that, I want to see on average, on expectation, what is going to be the information content, right? Not just for one event, but I'm drawing from the source, right? And so therefore, I'm going to have the sum over all the possible events, and I'm going to compute an expectation, right? It's the expected information content, so it's the expectation that I get event probably xi, okay? And this was earlier just exactly our definition of the Shannon entropy, right? And this is where it comes from. This is the information content of any particular event, and this is the probability, of event xi, right? So this is just an expectation. Okay, so this is why, throughout the lecture so far, I've been referring to the entropy as the expected or the average information content of a source. Okay, and that's where it comes from. So that's all I want to say about classical entropy now. Okay, and of course now we want to think about quantum entropy. So in the quantum setting, we named entropy after a different person, but it's really based on the same concept, let's be clear. The only question is, how do you extend this definition now to density operators rather than classical distributions? Okay? Okay, so the von Neumann entropy, just to be clear, will, instead of saying h of x, will instead denote it as, denoted s of rho. Okay, so it's going to be a function that's defined on density operators. Okay, so to kind of motivate this, like how are we going to go from something that's defined on distributions, the Shannon entropy, to something that's defined on density operators? Now let's see where density operators fit into this magic hierarchy we defined earlier of operators and how they generalize classes of real numbers, right? So let's recall that we started with Hermitian operators. So Hermitian ops, right? And henceforth I'll often just denote this class as Herm of operators acting on CD, so D by D Hermitian matrices. So these generalize the real numbers. Okay, so remember this meant that they're diagonalizable in particular, and their eigenvalues are all real numbers. Then we said, okay, well, how about we think about PSD ops? Okay, so let's denote this henceforth as pos of D, CD. These generalize the non-negative reals. Okay. And then we talked about projectors, right? Or orthogonal projectors, more accurately. And these all denote pi of CD. These generalize the set just 0, 1. Okay. And now let's think about what density operators generalize. Okay, so density operators. And these I'll denote often just as D of CD. Okay, what do they generalize? Well, okay, let's see, right? So they're Hermitian, right? So their eigenvalues are real. They're in fact positive, so in fact their eigenvalues are non-negative, but they also have a trace constraint, right? So the sum of the eigenvalues is 1. So the eigenvalues basically are non-negative and they sum to 1. So the eigenvalues are nothing other than a distribution, right? Their evals are a probability distribution, okay, non-negative and sum to 1. Okay, so therefore, we think of these guys as generalizing classical distributions, right? So in particular, any density operator, what is it? It's just like you take your favorite distribution, you embed it on the diagonal, okay, and then you could rotate it according to whatever unitary matrix you like. Okay, so you just change the basis so it doesn't look classical anymore. Okay, so the point of this discussion is that a density operator generalizes the class of classical probability distributions. Okay, and now that I've told you that, now it should be pretty clear what at least a naive, most natural way of generalizing classical entropy, Shannon entropy, to the quantum setting should be, right? Because the Shannon entropy was just defined on classical distributions, and hiding in any density operator on the eigenvalues themselves are a classical distribution, right? So obviously we're going to say, let's just apply the entropy function, the classical entropy function, to the eigenvalues of a quantum density operator. Okay, as an exercise, I won't do it here, but if you set, let me make a note. If U equals to identity, then we just have a classical. Then rho embeds or encodes a classical distribution. Okay, so then you just have some diagonal thing, and you can convince yourself that that thing is certainly PSD and trace 1. Okay, so diagonal means classical. Okay, so since so based on what I told you, let's just define the von Neumann entropy. Von Neumann entropy S of rho. Okay, and the way we're going to define it is we're going to define it. Let's assume that rho has spectral decomposition. Rho equals sum over I, lambda I. Okay. So now I'm going to define it as just the Shannon entropy, right, over the eigenvalues, lambda I, basically. I equals to 1 up to, let's suppose we're working over dimension D of rho. Okay. That's going to be my definition. Okay, so we can also write it as the following, right? The sum over I. Okay, just plug in the definition. Sorry, I'm not doing anything special here. Log of lambda I. Okay, and minus sign in front, don't forget. Okay, so that is the definition of the von Neumann entropy for quantum states. Okay, good. Now, so this definition is a little bit cumbersome. I mean, it totally makes sense, and a lot of times this is, well, okay, not a lot of times. This is, in fact, how you would compute the entropy. But we can write it in a slightly cleaner way, okay? And it turns out that we can write it just directly using the density operator in some sense without, explicitly writing out the eigenvalues. Okay, and for that, I'm going to have to take a detour into operator functions. And these are very important to define because they'll get used all over the place, including later when it comes to our distillation protocol. Okay, so operator functions are, the reason why I'm talking about operator functions now in particular is because, what I've just done, this idea of, taking some classical function, right, defined on the reals, and extending it to density operators by applying the function to the diagonal elements, right, that's what I did over here, to the eigenvalues, I should say. That is exactly what an operator function does. So it's very natural to make the segue now anyway. Okay, so here's the question. Let me formalize it. So given a function f, right, and it maps you from the reals to the reals. So this is a classical function, right? How to extend, quote unquote, f to its generalization, right? Because the real numbers are generalized by Hermitian operators. So how do we extend the function f to this more general space, to Hermitian operators? H in, okay. And the short and the long of the story is that what we'll do is that we'll always apply the function f to the eigenvalues of h. Okay. Okay, so the idea here is apply f to the eigenvalues of h, right? And that's well defined because the eigenvalues are just real numbers. F knows exactly what to do on real numbers, right? So let me be a little bit more precise and let's consider a concrete example, right? And let's also see why this works, basically. This example will be very good for this. So let's look at an example, right? F of x equals to everybody's favorite function, right? The exponential function, e to the x. Okay? And recall, okay, that the Taylor series, yes, I said the word Taylor series, right? Of f of x equal to e to the x is what? Is the following, right? Is the sum for n equals to 0 up to infinity, x to the power n over n factorial. Right, and let me just expand out the first few terms. X squared over 2 factorial plus x cubed over 3 factorial and so forth. Okay, so Taylor series, whenever you're dealing with a function that's kind of nasty, like an exponential, a sine function, a log function, it's always much easier, or typically much easier, to work with polynomials, right? And so the Taylor series gives you some way of making that conversion to a polynomial. And you have to be a little bit careful, of course, because you have to worry about in which range a Taylor series actually converges, right, to the right value of your function. E to the x is particularly nice because it will always converge for any value of x. Okay, so our discussion is particularly simple here. Okay, so if I'm looking at the Taylor series expansion of this function f of x, okay, what might lead us to this idea now that if I want to think about f applied to a Hermitian matrix H, I should apply f to the eigenvalues of H? Well, let's be stupid, right? The best way to come up with a good idea is just be naive in the beginning and just try the simple ideas first, right? Before you try anything complicated. Since I have a Taylor series expansion for f of x, why don't we try for Hermitian x, or sorry, H, Hermitian, sorry. Let's define f of h just in terms of this function. Let me define e to the power h, right, as a Taylor series, right, of 1 over n factorial, which is just a scalar, times the matrix h to the power n, which is also well defined. You just multiply h by itself n times, right? So, that's completely well defined. Let's be clear that the term 1 here, of course, gets replaced with an identity. That's the matrix analog of 1. That's the unit element. Okay, and then I have plus h, right? Then I have plus 1 over 2 factorial times h squared plus 1 over 3 factorial times h cubed, and so forth, right? So this expression here is completely well defined, right? What's on the right-hand side is completely well defined. The real question is, does this sort of make sense? In particular, is it captured by instead taking h and applying the exponential function to each of its eigenvalues? Okay, so this is an exercise in the notes. Let me just briefly sketch it because I think it's good to see this. Okay, I'll let you finish the formalization. So, so suppose that h just looks like the sum over I of lambda I, lambda I, lambda I. Okay. And so we want to show that, here's let me call this equation 7 just to match the notes. This exercise says that in equation 7, e to the h, the way I've defined it, if you just plug in the spectral decomposition into this Taylor series expansion, you'll get exactly the expression sum over I e to the lambda I, lambda I, lambda I. Okay, so remember here that these are the evacs, right? And here what I've done is I've applied the exponential function, right, to the eigenvalue lambda I. Okay, so in this case, little f was the exponential function e. Okay. So let's just verify that, when I do this naive definition of the Taylor series expansion, I really recover this idea that to generalize the exponential function to matrices, I just apply it to the eigenvalues. Okay. So why is this true? Well, let's just pick one of the terms in this expansion and just get a sense of how this works. Okay, so let me I won't do the full thing, but let's just do one term. Pick a term in the expansion. So let's, for example, look at 1 over 3 factorial h cubed, right? What is this thing equal to? So this is 1 over 3 factorial times, now h cubed is what? It's going to be the sum over I of lambda I. Here's the spectral decomposition, right? All cubed. Okay. And now, now we use the power of the spectral decomposition, right? If I take this expression here and I multiply it by itself 3 times, right? I'm going to need 3 indices, right? I'm going to need 3 sums, like I, j, k, for example. But this is an orthonormal basis, right? So when I expand out these 3 brackets, you're going to have a Kronecker delta showing up, right? That is going to make sure that in all 3 brackets, basically, you get the same term appearing. So in particular, what this means is that, I'll let you work through the details, right? But this will be nothing other than the sum over I, a single copy of this operator. Okay, so no more cube at the top, but the cube instead comes inside. Okay, because whenever lambda I is not equal to lambda j, the inner product will cancel. Otherwise, or will go to 0. Otherwise, the inner product will go to 1, and you'll start adding the exponents. Okay. Okay, so this is just for one expression here. If I look at this one over here, right, the h cubed expression really just looks like this. It looks like 1 over 3 factorial times the sum over I lambda I cubed times my original sum over these projectors. And so what you're seeing is, the action of this expansion is really just accumulating on the eigenvalues, right? So if I want to be a little bit more precise in this, right, what's happening here is I'm getting lambda I cubed over 3 factorial. Okay, this is a little bit more suggestive way of writing this. Okay, and this will be the same for all the terms, right? For every term in the expansion, you'll have, instead of cubed, you'll have the corresponding value of I guess, or sorry, n in the expansion. Okay, so here's the part where the function is really being applied. It's really being applied on the eigenvalues, right? And so you can factor out these eigenvectors. So, let me maybe be a little bit more precise here. This Taylor series expansion is nothing other than, the sum over n equals to 0 up to infinity. If you work through the details, you'll get the following. You will get the sum over, yeah, so now I do the sum over I of what? It's going to be lambda I over 3 factorial, all, sorry, this is not a 3 anymore. I really want to do it like this, n factorial, right? All to the power n times lambda I, lambda I. Okay. And of course now, this sum here only depends on this term here. It doesn't depend at all on the eigenvector, so I can move it in. Sum over I, sum over n equals 0 up to infinity of lambda I over n factorial all to the power n, lambda I, lambda I. Okay? And what is this thing? Well, that's just the function e to the power x, right? That is the exponential function. So this is nothing other than e to the lambda I. Okay, so just invert the Taylor series. Okay, so indeed, the way we define e to the h naively using this Taylor expansion completely recovers this idea that we just apply the function to the eigenvalues. Okay, so here we're really using, of course, the fact that the operator, so first of all, the operator is Hermitian, so we can apply a real valued function onto it, onto the eigenvalues. We're also using the fact that Hermitian operators always have an orthonormal basis. That was important to make sure that this powering trick worked right. Okay, so that the power would transfer from here to here. Okay. Good. So using this idea of operator functions, we can also do the same thing. We can also have an operator function, not say for the exponential, but also for the log function, right? You just apply the log now to the eigenvalues of the Ear density operator. Okay, so setting instead f of x to be equal to the log of x, right? So now we can define the operator function, or not we can find, we get now the operator function. I've already told you how to define it. Basically log of rho, okay? And then, and therefore, the entropy function from before, I'll let you convince yourself of this. You can now rewrite it, right? Before I had written it like this, minus the sum over I of the eigenvalues times the log of the eigenvalues. And now you could just simply rewrite it as minus the trace of rho times the log of rho. Okay? And you'll notice how both of these, of course, are going to be density operators acting on CD, right? I mean, otherwise this product would not make sense. Okay? So I'll let you verify that, this equation here, 8, I'll let you verify, this is an exercise, that indeed this is true. Okay, and in order to verify this, I mean, you're just going to have to do the expansion of this in terms of its eigenvalues, right? Just like we defined it, and just play with the terms, just basic algebra till you get it. Okay. Okay, so that's the notion of operator functions. That's how it applies to simplify the expression for the entropy function. Okay, quantum entropy function. I do want to point out one other operator function which gets used quite often and which we will use later in this lecture, which is the square root function. Okay, so let f of x equal to square root x. Okay, and again, this is a real valued function. Okay, and so so now I want you to instead apply, what is f of, say, Pauli z. Okay, let's do a concrete example now. Okay, so remember, what I want to do is I want to look at the eigenvalues of z. I want to diagonalize z, and I want to apply the function f, which in this case is a square root, to the eigenvalues of z. Okay, so what is that, right? Well, remember that z is what? It's just equal to 0, 0, right, minus 1, 1. That is the spectral decomposition, right? It just looks like 1 minus 1. So it's diagonal. You're staring at the spectral decomposition. Okay? And so I want to apply the function now to the eigenvalues. Here they are. Okay? So what does that mean? That means that if I think about square root of z, what I want to do is I want to take, square root of 1 here, technically. Right? So in this formalism here, square root 1, 0, 0. And I want to take square root of minus 1. Okay, so 0, 0. Plus the square root of minus 1 times 1, 1. Okay? So that's the definition of square root of z. Okay, so now we have to be a little bit careful here, right? Because technically speaking, these square roots are not well defined, right? I mean, they are well defined, but there's more than one answer, right? For example, 1 has 2 square roots, right? 1 and -1, both square root of 1. And same thing with -1. -1 also has 2 square roots, right? So here's -1 on the unit circle, right? I minus I, right? So if I want to come up with -1, 1 square root is of course I, right? That's how we define I, because I could do this rotation twice and I can get -1. So one possible definition for this thing, I could have defined this as 0, 1, 0, 0, I, and that's a completely valid definition for square root of z, because if I square this matrix, I will get z back, right? But I could have also defined it in a different way, as I could have looked at the other square root of -1, right? The other square root of -1 is this one. Let me do it in a different color. So it's this, right? It's -I. Because if I do that rotation twice, I'll end up at -1 again. So I could have also, defined the square root of z as 1, 0, 0, -I. And you'll notice these are not the same matrix, right? In the sense that, they're not the same up to some multiplication by some scalar, okay? So the point of this is, number one, I wanted to just do an explicit example of how you compute, an operator function. And in this case, it's particularly easy to compute because z is already diagonal, okay? And I want to point out that, these operator functions might not in general always be uniquely defined, right? Okay, so the square root of an operator is not necessarily unique, but the key point, of course, is that it doesn't matter which of these two I choose. If I square either of those operators, I'll get z back, right? Which is intuitively or logically, that's exactly what you expect square root of z to do. Okay, so note, regardless which definition of square root z I choose, if I square that definition, right, I will get back identity. Okay, so of course you want to fix your definition and apply it twice. Okay. So in that sense, we really do recover the intuition behind the square root function. Okay, and I'll let you just verify that this holds. Just do this calculation and just verify that this holds. Wait, let me convince myself that this is true. Oh, sorry, that's correct. Yes, that's right. Good. Okay, so that's the von Neumann entropy. And now I want to talk about the properties of the von Neumann entropy. Okay, so let me just briefly recap everything that's happened, right? We defined, the Shannon entropy for a distribution to be, let's go back up and show you, right? The Shannon entropy of a distribution, remember, was just this thing, right? The sum over the probability of each event times log of 1 over the probability, denoted h of x. And so since this was defined on probability distributions, we said, aha, look, density operators are really just probability distributions in disguise. You're just changing the basis in which you view the distribution. So we can define the von Neumann entropy as just the classical entropy on the eigenvalues of the operator. And once we did that, then I said, okay, look, let me introduce you to this notion of an operator function, which is exactly, by the way, which is what this is doing, which is you have some function and a classical function, a real valued function. To extend it to operators, you just define that function to the eigenvalues, which is what we did here. Okay? And in doing so, we could rewrite the Shannon entropy in a nice way. We could just rewrite it compactly as minus trace of rho times the log of rho, where log is being applied to a matrix now. It's an operator function. Okay? So let's return to the entropy now. Let's think about properties of the von Neumann entropy. And I won't discuss all of them, but maybe the ones that will be most relevant to us. Okay, so here's a question. When does a quantum state have no entropy? Okay, so when is S of rho equal to 0? Okay. Okay, so let's go back to the classical case. So which kind of distributions had no entropy classically? Well, these were the ones like the biased coin, in which there was zero certainty at all, right? You knew exactly what was going to happen. Okay, so in particular, you had a singleton distribution, right? There's only one outcome with non-zero probability. Okay, so the quantum analog of this is going to be what? It's going to be the case where S of rho is equal to 0 if and only if rho is a pure state. Okay, so meaning rho, sorry, not P, rho is equal to just some projector on some unit vector psi. Okay, for some, doesn't matter which one, it's just got to be a unit vector, of course, otherwise it's not a density operator. Okay, so this is the class of states for which the entropy will be 0. Okay, so why is this true intuitively? Well, this is because I know exactly what state my system is in, right? It's in the state psi, right? There's no mixture here. There's no uncertainty. I didn't flip a coin and prepare one state or another. This is not to be confused with the idea that, of course, if I measure psi now, I will induce a distribution, right? That's a different story, right? Because when I measure, I don't have psi anymore, right? I've destroyed psi. Okay? So pure states are zero entropy states. Okay? And, I'll let you kind of work that out. Well, okay, let's just do it quickly because it's not difficult to do, right? So let's suppose psi is in C2, okay, just for simplicity, okay? And consider rho, which is a projector onto psi, right? That's my density operator. And now, I want to write it as a spectral decomposition. So it's the eigenvalue 1 times this thing, right? Plus the eigenvalue 0. And here, I can choose any, orthogonal basis for the remainder of the space. And since I'm working over C2, there's some state, psi perp, which is kind of the unique state orthogonal to psi, right? So in C2, doesn't matter whatever psi is, right? There's always some orthogonal state, a unique one that is orthogonal in C2, okay? Psi perp, sorry. Of course, I can take psi perp and multiply it by something on the unit circle, and it's still going to be orthogonal. So it's unique up to scaling, okay? The exact choice of psi perp, of course, does not matter because, I have a 0 in front, right? So I'm just writing this for completeness because now if I want to consider the entropy of rho, remember, what is it really going to be? I'm going to take the exact same thing and I'm going to apply the classical entropy function to the eigenvalues, right? So it's going to be eigenvalue 1, right? Here it is, times the log of, sorry, I should have the log of 1, right? Minus this eigenvalue, here it is, 0 times the log of 0. Okay, and so the log of 1 is 0, right? So this whole thing goes to 0, and we define 0 log 0 to be 0. Okay, so ta-da, pure states have entropy 0, as claimed. Okay, so that's the first case we're going to care about. Let's think about the second case. Sorry, the second property. So we talked about when a quantum state has no entropy. Let's do the other extreme. So when does a quantum state have maximum entropy? Okay. And classically, we saw that, when we did a fair coin flip, we got entropy 1. And it turns out that that is the unique distribution, like probably a half and a half, that gives you the maximum entropy over a single bit. Okay. So the quantum analog of this, of course, of a fair coin flip is just the maximally mixed state, right? So quantumly, rho equals to the maximally mixed state is the unique state. This is, I'm talking, of course, density operators on C2 here, maximizing an entropy of rho. Okay, because it's the most uncertainty. I know absolutely nothing about my state. Okay, so both eigenvalues are half, right? So that's why, of course, this thing generalizes the coin flip, because both eigenvalues of identity over 2 are half. And this generalizes more generally. The corresponding maximum mixed state in any dimension. So here I'll put CD maximizes S of rho, okay, in that dimension. Okay, so I'll let you kind of work out as an exercise. Maybe you can do it yourself, or we can do it in the tutorial. You can just bug me in the tutorial to do it. But what is the entropy of this guy here? Identity over D. Okay. Okay, the third one is that quantum information, the third property is non-negative, right? And this was also true for the Shannon entropy, right? And since all we did was we took the Shannon entropy, we applied it to the eigenvalues of this density operator, that means that you know, the von Neumann entropy will also be non-negative. We just get this immediately. So immediate from the use of Shannon entropy. Okay. Okay. The one that's maybe a little bit less trivial is, you know, we said the log function was really nice for the Shannon entropy because it ensured that if I had two independent probability distributions, then their information content jointly was additive. Okay, it was the information content of X plus the information content of Y. So what is the analog of this statement quantumly? All right, so what is the quantum analog? Maybe I should spell this out. The quantum analog of independent distributions, X and Y. Okay. Okay, so the quantum analog is, well, you know, first I have two density operators, right? Each of which is encoding some distribution, right? Just in a funny basis. Then basically rho and sigma are independent if, can you guess what kind of, how I'm going to stitch these two states together? Take a moment to think about it. Okay. If their joint state, rho AB basically, so I can imagine they're acting on two states. This is defined as rho A tensor sigma B. Okay, so that is the analogous notion of independence quantumly. Okay. So tensor product. Okay, so the two systems have nothing to do with one another. And, you know, as an exercise, you know, I'll get you to prove that indeed, now if I take the entropy of a tensor product state, right, that it is additive, right? It's going to be the entropy of rho, the information content of rho, basically, plus the information content of sigma, if you will. Okay? So that generalizes the classical property we wanted of additivity over independent distributions. Okay? And here, it's probably going to be useful here to recall. So if you do this exercise, I strongly recommend you do it. You know, how do you think about, so over here, right, if I look at the entropy, right, what I'm going to do is I'm going to diagonalize rho tensor sigma, right, and apply the entropy function to the eigenvalues, or the, to the classical entropy function to the eigenvalues of the joint state, rho tensor sigma. So what is the eigenbasis of rho tensor sigma? Well, recall that the eigenvectors, recall that if I have eigenbases, psi I on A and phi I on B, that implies that psi I tensor phi j is an eigenbasis on the joint system. Okay, so if you want to think about you know, the spectral decomposition of rho AB jointly, you can do it just by knowing the spectral decomposition of these guys individually and just taking the tensor of their eigenvectors. Okay, so that'll probably be useful in proving this identity. Okay, so I don't want to focus too much more on properties of the entropy. Let me just state two more briefly, because it's nice to know them, but we're not going to go into them. So the fifth one is subadditivity. Okay, so subadditivity says the following. So here, if the state was, the joint state was in, you know, if I had rho A, rho B, right, then I could just do this. The joint state, when it's in tensor product, so it's independent of two subsystems, you just add the information or the uncertainty, okay? But what happens when A and B are not in tensor product? What happens if I have a joint system that's entangled across these two? What's the relationship between the left side and the right side here? And subadditivity says, there's still something you can say. You won't get equality, but you'll get at least an upper bound. Okay, so the joint entropy is at most the sum of the entropies. So that's nice to keep in mind. And the other one I want to mention is concavity, right? So this says that if you have the entropy of, a mixture of density operators, how do you think about that, right? So here you have to be careful, right? Because normally, if I was evaluating entropy on a single density operator, right, I can hopefully diagonalize it and off I go, right? I just apply the classical entropy function to the eigenvalues. But now, in general, if I know the spectral decompositions of each row I in the sum, it doesn't necessarily mean that I know the joint spectral decomposition over all n terms, right? Because when I add these operators in there, they diagonalize in different bases, the total sum might diagonalize in yet a completely different basis, okay? So it's nice to be able to relate, the entropy of the full thing into the entropies of the individual ones, because at least I can maybe diagonalize the individual operators row I alone. And then you can maybe think about using the concavity formula, which says you can move the sum out and just think about the entropy of each individual operator. Okay, and here I'm assuming, of course, that the set pi is a distribution. Okay. Okay, and by the way, in general, in the course, when I say row A, if it's not clear from context, like here, I really meant that this is the operator. Well, okay, I think it's consistent, right? It's going to be the trace out of B. If I have a joint state system on row AB, and I trace out B, and I'm always going to use row A to denote that reduced state. Okay. Okay, so that is everything I want to say about defining entropy, talking about entropy, enjoying the various flavors of entropy, right? Now let's actually use entropy for something meaningful, right? We are not, at the end of the day, of course, this is not a math course, right? We are doing computer science, so we like to apply these things. Sorry, maybe let me write it this way. So to quantifying entanglement in composite quantum systems. Okay, so what was this all about? Or what is this all about? So here's the main question, right? This section is asking. Okay, so generally speaking, entanglement is nowadays known to be a valuable resource to do all sorts of tasks like communication, like with teleportation, or to get exponential speedups in pure state quantum computation. So the most natural question you might ask is, of course, given the state I'm preparing in the lab, is it even entangled to begin with, right? So given a joint state rho AB that acts on the density operators acting on, let's just assume our subsystems have the same dimension, doesn't really matter, right? Is rho AB entangled? And here I need to be careful. Entangled across, I have to tell you which cut I'm talking about. So here it's pretty simple because there are only two subsystems the way I've written it. But if I had n qubits, for example, I could partition those n qubits into any pair of sets I like, and then I can think about the entanglement across that cut. Okay. So, what is the complexity of answering this question? Okay, and here let me just recall that we say rho AB is not, or it's unentangled or separable or unentangled, if and only if I could write it as a mixture or a convex combination, right? We talked about this terminology last class. A convex combination of product states, right? Sum over I. pi rho a I tensor rho b comma I. Okay, so if and only if I can write it as a convex combination of product states. Okay. Okay, so generally speaking, okay, so generally, deciding if rho AB is entangled, okay, is actually NP hard. Okay, it's NP complete, depending on how you phrase the question, but you know, it's more or less NP complete. Okay. So it's actually very hard to figure out if, you know, I give you a matrix, you know, can you decompose it as a sum of this form? Now you might be thinking back earlier, you know, in one of the earlier lectures, we said, oh, you know, well, for pure states, we can tell if a state is entangled or not. You know, what's this NP hardness business? And indeed, that's right, right? So in the special case, so but if rho AB is pure, okay, i.e. rho AB is, you know, some projector onto some pure state vector psi b, then we can decide separability, right? And so what tool did we use? So we did this in class. We used the Schmidt decomposition, right? Okay, so that's just a reminder now. Okay, and so remember that the Schmidt decomposition, what did we say? Here's the Schmidt decomposition. Again, so this is just a recollection, right? Let's recall that the Schmidt decomposition of psi AB is what? It's just going to be the sum over I. And here, let me be consistent with my course notes. I'm assuming both my systems are in d dimensions. I have d non-negative terms Si, and then I have orthonormal bases Ai and Bi. So remember, these are non-negative. These guys are orthonormal bases. Okay, for their respective spaces CD and CD. Okay, and what we said in class was that we said that, well, first we said that, you know, psi AB is entangled if and only if strictly more than one of these Schmidt coefficients, these are the Schmidt coefficients, Si, if and only if at least two of those Schmidt coefficients is non-zero. That's how we defined entanglement, right? So equivalently, I believe this was an exercise in those lecture notes. We said that psi AB is entangled if and only if I take the partial trace, I trace out half of this thing, and I look at the rank of this operator now, if and only if the rank of this thing is at least 2. That was an exercise in one of the previous lecture notes. This rank condition is completely equivalent to counting the number of non-zero Schmidt coefficients. Okay, and this, you know, we've covered this, and now this gave us a criteria to say yes, for pure states we can say something, right? Yes, state psi b is or is not entangled, but now we want to go a bit further, right? Because, you know, for example, when we were talking about the teleportation protocol, we saw in the exercises, or for the homework exercise, right, that it was important that that state we shared was really, you know, so-called maximally entangled, right? The coefficients were balanced, 1 over 2, 1 over 2, right? And we saw that if you change the balance on those coefficients, right, the probability, or well, the teleportation protocol, generally speaking, begins to break down, right? So we do, ideally, we would like to have a way of quantifying how much entanglement is in a quantum state, and for that we can use the entropy, right? So why is that, right? Well, intuitively, the reason is because of the following, right? So let's remember that when we talked about Schmidt coefficients, right, For example, in the Bell state, I had two Schmidt coefficients. They were both 1 over root 2. They were both balanced. And then, we thought of the state as being very highly entangled. Whereas if I had a product state like something like this, 0, 0, right, then there's really only a 1 Schmidt coefficient, right? It's like a 1, and then I have 0, 0 times, whatever state I want to put here, let's say 1, 1, right? And this is not entangled at all, right? It's a product state. And so here the coefficients are highly unbalanced, or imbalanced, I should say. You'd think I know how to speak English. Okay, and so, we need a function somehow that distinguishes between when the coefficients are nice and balanced versus when the coefficients are really highly imbalanced, right? But that's exactly what the entropy function does, right? We saw that with the fair coin flip where the probabilities were both balanced to half each, versus when you had a highly biased coin flip where the probabilities were highly imbalanced, right? So that's why intuitively entropy will work here, right? So in particular, instead of just looking at the rank of this reduced state, if I look at the entropy of it, it'll give me a more fine-grained notion of just how much entanglement is in the state. Okay, and okay, therefore, so we'll define, so this is a definition, the entanglement entropy, E, and I'm going to really make sure that I put in a pure state here, because it only works on pure states. We'll see that in a second. So I'm going to define this thing as the entropy of precisely the reduced state of psi AB, psi AB. Okay, so that is the definition of the entanglement entropy. So if you want to know how much entanglement is in a pure state, throw out half the system and compute not just the rank, but compute now, the rank will tell you if it's entangled or not, but compute the entropy, and that'll give you a more accurate picture of just how much entanglement is in the state. So let's just do a very quick sanity check as an example, right? So what's the entropy of the Bell state, right? Let's just 2-qubit Bell state. So what is that? It's the entropy, right, of the partial trace version of the reduced state of this thing here, right? Okay, but we know what the partial trace of the Bell state is, right? This we've memorized by now. It's just the identity operator. So this is just going to be the entropy of the identity over 2, right? The maximally mixed state. And the identity over 2 is nothing. It's just, I'm sorry, it's not nothing. It's nothing other than a classical coin flip, right? It's just a half and a half on the diagonal. So this is really just the same entropies you'd get for an unbiased coin flip. And we saw earlier that an unbiased coin flip, right, to transmit that the outcome of that from Alice to Bob, on average you have to transmit 1 bit of information. The entropy is 1. Okay. So let me be clear. Just an observation. Here I chose to trace out the B system. Actually, it doesn't matter which one you trace out. In both cases, you'll get the same value. Okay, and now the question is why, right? Let me just do an observation, and this is a nice exercise for you to think about. It's not in the course notes, actually. So the entropy of, if I trace out B of psi, right, that actually equals to the entropy if I trace out A. Okay, I'm claiming this. I haven't proved it, but I'll let you think about why this is true. Okay, the entropy is the same, even though, okay, let me be very, very clear, all right? These two density operators themselves might not equal to each other. Huh. Okay? So even though the density operators, when I do the reduction, if I look at the left or the right, those might actually look like different density operators. Nevertheless, the entropy is the same. Okay, and so I'll let you think about why this is true. So this is, of course, in general. This, in some cases, of course, they can be equal. But the intuition, of course, is that, think about what the entropy function is defined on, right? There are two parts to the density operator, right? The eigenvalues and the eigenvectors. So where did we define the entropy on, right? We didn't define them on both. Okay, so in particular, you'll notice that, to prove this, basically, just observe, when you do these partial traces on A or B, which parts of the spectrum or the spectral decomposition of your state changes and which part stays invariant. Okay. So I'll leave that to do as an exercise, however. Okay. So let me do one thing just to clarify, because I mean it's a little bit still, I think, mysterious, and well, okay, to be fair, entropy is always a bit of a mysterious thing to play with. But I said that phi plus, we already computed the entropy of this thing, right? And my intuition I stated here was that the more balanced these Schmidt coefficients are, right, the more entangled your state is going to be, right? And I claim that the entropy function is going to capture this. There's of course one hitch to this, right? And the hitch is that 1 over root 2 plus 1 over root 2, that doesn't sum to 1, right? This is not, the amplitudes are not a distribution, right? In order to get a distribution, I have to take absolute values, sum and square these guys, right? Then they sum to 1, okay? So how come applying the entropy worked, right? Because, amplitudes are not a distribution, right? So, so note that, 1 over root 2 is not a distribution. Okay. And this is intuitively why we do that partial trace part. This is why throwing out over here, when I trace out B, what it's doing is it's going to convert these Schmidt coefficients into probability distributions. Okay, or elements, probabilities in a probability distribution. And let's just see why, right? So the trace out of B converts the amplitudes to probabilities such that applying the entropy function makes sense. Okay, so let's see why this is true. Suppose I want to trace out how do I want to do this? Okay, yeah. So suppose I want to trace out, I have some state with some Schmidt decomposition. Let's just work in 2 qubits to keep life simple. So I've got, say, alpha 0, 0 plus beta 1, 1. Okay, I'm going to be as general as possible here. Alpha star 0, 0 plus beta star 1, 1. Okay, and I just said I'm going to be as general as possible. Of course, I'm cheating a bit here because technically speaking, I don't know that the most general states will not have 0 and 0 as their Schmidt vectors here, for example. There'll be some other Schmidt basis, but it turns out that all of these, like the entanglement entropy, does not care about local changes of basis, right? So I could always rotate the local Schmidt bases to look like 0, 0 and 1, 1 if I want. Okay, and the entanglement entropy will not change of my state. Okay, so as an aside, also a nice exercise, entanglement entropy is invariant under conjugation by unitary. By local unitary. That's important. Okay, so in other words, the entanglement entropy of state psi AB is equal to the entanglement entropy of UA tensor VB, any unitaries you like, doesn't change. Okay, so that's just a nice aside. I'll let you prove that on your own. Okay, so this is why I'm assuming without loss of generality that the bases just look like 0, 0 and 1, 1. Okay, because I could always pre-rotate them first, since we're just talking about entanglement entropy. Okay, so what is this thing? Well, this is just going to be trace out a B of absolute value of alpha squared 0, 0, 0, 0 plus alpha beta star 0, 0, 1, 1 plus alpha star beta 1, 1, 0, 0 plus beta star, alpha beta squared, absolute value of beta squared 1, 1, 1, 1. Okay. And now when I check the partial trace, like the terms that are going to go to 0 are going to be this term, right? And this term, right? Because here I have a 0 on the left and a 1 on the right. the second second subsystem, the one I'm tracing out. Okay, and then you'll see exactly why things turn into probabilities, right? Because then I'll get 0, 0 plus beta squared 1, 1. Okay, this is a spectral decomposition of what's left because here these are orthonormal bases, right? Orthonormal basis vectors 0 and 1. And you'll notice that the amplitudes alpha and beta, what's happened to them is that they've become, I took absolute value of alpha squared, absolute value of beta squared. So they've been converted into probabilities now. And now these things certainly sum to 1. Why? Well, because these are amplitudes, they sum in square to 1, right? By definition, that's a unit vector. So now these are probabilities. Okay, yay. Okay, so this is why it makes sense now to apply to this reduced state the von Neumann entropy map or function, right? Even though it wouldn't make sense to directly apply it to state vector. Good. So the point of this discussion is that if you want to understand how much entanglement is in a quantum state, a pure quantum state, a bipartite pure quantum state, let me be very clear, things get more complicated when you go to multi-party systems, okay? But at least in the bipartite pure state case, this always works. And let me also make a note that more or less the entanglement entropy, so this function E of psi is for pure states, is the unique measure of entanglement. And I think you need to be a little bit careful how you define a measure of entanglement, right? It needs to satisfy certain properties, but at the level of discussion we're doing now, let's just leave it at this, right? And this is, however, for pure and bipartite states. Okay, so when you leave either of these two settings, when you're no longer pure states or bipartite states, let's say you're talking about tripartite states, then this statement is no longer true. Okay, so the bipartite pure state setting is kind of a very special case. Okay, finally, let me deviate from this. Okay, why pure? Okay, so the first thing you should be doing when you're kind of listening to this lecture is like you should be saying, okay, look, why? Let's just be naive. Let's just apply this entanglement entropy function to a mixed state and let's see what happens. Like, why does it not work for non-pure states, right? So let's do that. Let's play. All right, let's do an example. All right, so let's imagine that I set rho AB to be just the identity matrix, which is what? Of course, it's just the tensor product of two identities, right? And let's extend. I defined it technically, the entanglement entropy on pure states, just to really stress that it should be defined on pure states for it to make sense. But of course, you could do the same thing for mixed states. Because it's nothing other than same thing. Just trace out half of your system, rho AB. So now this is a mixed state, more generally. So trace out half of it just like before, and then take the entropy, right? There's no magic here. Okay, so here's my claim. I'll let you work this out on your own. My claim is that the entropy of the identity over 4 is equal to 1. Okay? So why? Okay, well, I mean, this is easy, right? I mean, maybe I'll just quickly sketch it, right? The identity of 4 is just, the tensor product of identity over 2 with itself. So when I trace out half the system, really, what is this equal to? The identity over 4, this is just equal to, sorry, I should not have done this. This is what I wanted to write, right? So the entanglement entropy, okay, you know what? Let me just do it properly. And this is what? This is the entropy of identity over 2, tensor identity over 2. But then you need to do a partial trace in here, right? So there's a partial trace over B. So that's just the entropy of identity over 2. Okay, we just trace out the second subsystem. It's in tensor product, so this is easy. And this is just a fair coin flip, just one. Okay, so what is this telling us though, right? This is telling me that the maximally mixed state, right, which is certainly not entangled, okay, it's just complete noise, right? There's no correlation at all between the two subsystems. I mean, I just wrote it as a tensor product right here, right? So it's certainly not entangled. It still has, maximum entropy, right? It still gets entropy 1, which is supposed to be reserved for things like the Bell state, right? So here we see that, when you start applying this function here, when you extend it from pure states to mixed states, it's not really an accurate indicator anymore of entanglement. It still can say that really separable states, complete noise, looks very entangled according to this measure. Okay, and again, this is not surprising. Why is this not surprising? Because for mixed states, even in the bipartite setting, determining if a state is entangled or not is NP hard. Whereas this criteria here, this E, I could always evaluate this efficiently, right? I just do a partial trace and I compute the entropy, right? So that's polynomial time procedure. It should not work in general for mixed states, okay? Okay, so E mistakenly says identity over 2, tensor identity over 2, which is clearly a product state, is maximally entangled. Okay, and not surprising, since checking if mixed rho AB is entangled is NP complete. Okay, so there shouldn't be a polynomial time procedure like the entanglement entropy, for example, that can check if something mixed is entangled or not. Okay, so now that we've talked about how do we quantify the amount of entanglement in a quantum system, we can get greedy. We could ask, okay, well, can I have more entanglement, right? Can I get more entanglement? Given many copies of a quantum state, right? Can I convert that to yet another state which has even more entanglement than when I started with? Okay. And this is in particular important because in the lab, it's very difficult to actually prepare, say, a pure Bell state or something like this, right? And even if you could prepare it perfectly in a lab and then you have to send half of it over to Bob somewhere else, that sending process itself, that transmission itself is probably going to be noisy. And so the state you start, say, your teleportation protocol with is not, realistically speaking, it's not going to be working on pure states, okay? So it's very natural to ask if in the lab I'm able to prepare something that's, not too far from a Bell state, let's say, can I kind of purify, can I prepare many copies of that same state and then act on those joint copies at the same time to produce kind of, to concentrate or to purify out the pure state entanglement that I really want to have so that I can then run my teleportation protocol on something that's very close to an actual pure Bell state. So that's the basic idea of entanglement distillation, right? And that was the quote at the start of this lecture that said, can we distill entanglement? Or sorry, the quote at the start, this quote at the start of the lecture was about distilling water due to Aristotle, but that was the connection, right? That we're going to have some sort of noisy state that is entangled, but not that strongly, and we want to extract out more entanglement. Okay, so we have to be a bit careful about what it means to distill, like how do we formally model this, right? So in particular, obviously if I have a joint system, right, between two parties, but I can act on both parties together, let's say both parties are in my lab, right, then it's trivial to create more entanglement in the sense that, well, if I could just act on both parties simultaneously, assuming I could do perfect operations, well, I could just prepare a Bell state from scratch in some sense, right? There's no need for distillation, okay? The more interesting setting, of course, is that suppose, I do this transmission setting where I prepare a Bell state and I send half of it to Bob, and now we're each on different planets. We each share half of this Bell state, but now, during the transmission, the state became a bit corrupted. Can we purify it back to a proper Bell state, right? And so that's why the model in which we formalize the notion of distillation, in order for it to make sense and be well motivated, we think of in the settings of so-called local operations and classical communication. Okay, so also known as LOCC. Okay, so what does this mean? This means that we have two parties. Here's Alice. Here's Bob. Okay, and they're spatially separated. Okay, and so let me be clear. What do I mean by that? Like, what does it mean in terms of our operational framework, right? Spatially separated. So this means that they cannot apply a joint unitary. Okay, so this they cannot do, right? The only thing they could do is a local unitaries on both of their sides. Okay. So, what can they each do? Like Alice could apply, you know, a local unitary on her side if she likes. Bob can apply a local unitary on his side, right? And maybe between them they share many copies of some state rho AB. You know, they have many copies of this state, right? And then the other thing they can do, of course, is that, you know, they can pick up a phone and call each other, right? That's where this classical communication comes from. Okay, so they can both do local measurements, they can call each other. And the question is, through this back and forth kind of protocol, right? Can they, so given many copies of rho AB, can one distill, and this is using LOCC, right, in order for it to be non-trivial, a Bell state, let's say. So can you trade somehow your many copies of rho AB and just give me one Bell state in return, for example? Okay, so the answer is sometimes yes. Okay, actually I think for 2-qubit states the answer is always yes. Well, for 2-qubit entangled states, right, the answer is always yes. Certainly for pure states it's always yes. If you want to talk about mixed states, for 2-qubit states, any entangled mixed state turns out to be distillable. Okay, and when you start talking about Q-trits and higher, 3-dimensional, 3x3 systems and higher, then it starts to become non-trivial. Okay, so not all entangled states can be distilled. We'll talk about that a bit at the end. So the answer is sometimes yes. And this is always assuming a rho AB was entangled to start with. Oops. Right, because if rho AB was not entangled to start with, then there's no way you're going to be able to create entanglement using LOCC, right? Because you're just doing local operations and classical communication. So you need a joint unitary across both parties to create entanglement. Okay. Okay, so let me give you a simple, well, it's simple to state. It's, I think, quite mysterious in general, as is the topic of distillation in general. Okay. So let's see. So this is called the Recurrence Protocol. Okay. And so the input to this protocol is going to be a 2-qubit mixed state in general. This is some rho AB, a density operator acting on C2 tensor C2. And in general, you can imagine you're giving many copies of this. And the goal is to output the singlet state. And by singlet, one often is referring to the Bell state psi minus, which is this one. 1 over root 2, 0, 1, minus 1 over root 2, 1, 0. I mean, it's not very difficult to modify this protocol to work for other Bell states, but let's just stay with the original formulation of the protocol, right? And note that if our goal is to, say, run something like a teleportation, right, then typically we run teleportation not with this Bell state, but with the other one, 0, 0 plus 1, 1. And that's not a problem. I mean, once you get any of the 4 Bell states, you could always convert between them using just local operations. So, for example, if I want to convert into phi plus, right, so I can do my teleportation protocol, if I could only prepare psi minus, the singlet, then what I do is just an identity tensor y. So this is on AB, this is on AB, this is on AB. Right, so then it's very easy for me to do the conversion. Once we get the singlet, Bob can just do a Pauli y on his side, and we'll get the state we want to run the teleportation protocol. Okay, now for this particular protocol, I sort of said this earlier, but any 2-qubit mixed state, which is entangled, right, can always be distilled up to Bell states, basically, in the asymptotic limit of many copies. This particular protocol will not work, however, on any mixed state. It needs a precondition. So here's a precondition. The precondition is the following: that you have to be sufficiently close to the target, the singlet, to begin with. Okay, so let me define this thing here. So here's my state rho AB, the input state. Its overlap with psi minus to begin with, okay, so its expectation against it should be strictly larger than a half. Okay, this is the precondition. I'm going to give this a name because we're going to use it over and over. We're going to call it f of rho AB. Okay, so you'll notice how it's a function of rho AB, right? And, if you look at the literature, this thing, of course, has a name. It's something called the Fidelity Function, which has kind of a somewhat of a nasty definition more generally, but here it's a very special case of fidelity where we want to know the closeness between rho and the singlet psi minus. And when one of the states like psi minus is a pure state, the fidelity has this very nice form where it's just like the sandwich, basically. Okay, you don't need to know anything about the fidelity for this discussion. Okay, it's just f of rho AB equals this function here. So the overlap between a rho AB, your start state, and the singlet should be strictly larger than 1/2 for this protocol to work. Okay, and henceforth, where it'll simplify things, I'll just write f instead of f of rho AB. Okay. Okay. So the goal is to come up with a protocol that does this. Right, and let me set up the exact scenario. Okay, so let me draw a picture. So here's my Alice. Here's my Bob. Okay, and in this particular protocol, they start with 2 copies of their start state. Okay, so here's one copy. Here's another copy. Oh, why this is not switching colors? Okay, so here's so Alice, here's Bob. Okay, Alice has 2 copies of the subsystem A, right? Bob has 2 copies, so I'll label them B1, B2. The top copy here is going to be the state rho, but it's on A1, B1, and the bottom copy here that they share will be rho, but now it's on the second copies of the subsystems. Okay, so we have 2 2-qubit states, right? And you could view them either as, the Alice side versus the Bob side, or you could also view them as, the copy 1 versus copy 2, right? There are 2 ways to kind of bipartition this space. Okay, so the steps of the distillation protocol proceed as follows. Okay, so the first step is something called the twirling operation. Okay, so the twirling operation is essentially like picking a random Pauli matrix and then applying it, right? That's essentially what it is. One of the reasons why the twirling operation is useful is because it allows you to kind of move things into a standard form in some sense. And we'll see what I mean by that in a second. Of course, there's a bit of a loss because the map I'm applying is not really unitary, right? In order to do a twirling operation, as we'll see in a second, I have to flip a coin, right? Technically 2 coins, and pick one of the Pauli operators at random and apply that, right? So even if I started with a pure state, I now end up with a mixed state. So there's a bit of a loss in doing this twirling, but you also gain something. So let me formally specify what I mean by this. So Alice picks Pauli at random. So picks one of these Pauli operators from the set of all 4 Pauli operators, right, which are technically the identity is also included. Okay, that's just a picture here. And what she does, what does she do? She tells Bob her pick. Okay, so she picks one of these 4 at random with probably a quarter each, and she phones Bob up and says, okay, I picked Pauli X, okay? Okay, then they each locally apply. They don't apply exactly that, but they apply the square root of that. All right, so square root. Let me give this a name. Right, so suppose the name of the operator she picked was u, so u is maybe x in our example. Then they both apply square root u. And now square root u, notice how, so okay, well, they each apply square root u to each half of their subsystem on both their copies. Okay, so they apply it to row AI, BI, for I is in 1, 2, okay, because they each have both copies of the state. So that means that Bob, on the first copy, he applies square root x in our example, and then on the second copy, he also applies square root x. Okay, and remember, we defined the notion of an operator function earlier in this lecture. So square root u is defined exactly like that. U is not, well, the Pauli operators are Hermitian, but even if they weren't, this would be well defined because this notion of an operator function applies as long as you can diagonalize the state. Basically, you can try and apply the definition. Okay. Now, in the case of the Pauli operators, they are Hermitian, so we really have nothing to discuss here. Okay. So, but let me be clear that the state they obtain. So they have 2 states, right? To obtain joint states, right? So sigma A I BI. Okay, so I'm using an I here just because they'll have 2 copies of the state, right? And each copy of the state now looks like this, right? I started with this state that they shared, and then they each do square root u on A, tensor square root u on B, and same thing here, square root u on A, tensor square root u on B, and we have to do a dagger. Okay, so that's technically what's happening in this step. Okay, Alice picks a random Bell state, Pauli matrix, tells Bob her choice over the phone. Then they each locally apply half of a Pauli to their system. And so let me just make some remarks here. So notes. This random choice of Pauli, this random application. Well, it's a local application, right? Local application of Pauli's is a so-called twirling map. So, that's a thing. That's a well-defined twirling map. Okay, so that's a well-defined concept and people use it all the time. Okay, and we think of it as, it's a map that takes a density operator from, C2, tensor C2, right? And it maps it back into the space, right? And as I mentioned earlier, this map is actually not unitary. Not unitary. And this is because of due to the random coin flip. right? So indeed, each of the Paulis is unitary, of course, right? But I'm not picking a fixed Pauli, right? I'm flipping a coin, and based on that, I'm doing a Pauli. So there are multiple branches in which my mixture can be consisting of. Okay. So this type of map is something called, we talked about this during the tutorial. The most general type of map, which we won't really get into in this course, is not unitary actually, but it's something called the trace preserving completely positive map. Okay, and there's an entire formalism for dealing with this. We're not going to go there because it's not really necessary for this course. The main thing here to note is that any map you apply in quantum mechanics, it has to basically preserve the set of density operators, right? Otherwise, it makes no sense. So the two bare minimum necessary and sufficient conditions you need to do this are the map should be, aside from being linear, the map should be trace preserving. That's that. And the map should ensure that the positivity of your matrix is preserved. And that's this completely positive part, more or less. Right? There's more to it, but that's the rough idea. Okay? And as I also mentioned in the tutorial, without loss of generality, in fact, I haven't been lying to you this whole time. Anything you could do using these kind of more funny classes of maps which are non-unitary, you could always simulate on a larger space by using a unitary operator. Okay, so, but again, that discussion is not really necessary here, so let's not go on that tangent. The point is that in step 1 in this protocol, they basically each apply a fixed choice, random choice of Pauli operator, the same one on both sides. Okay, we'll square root of it. And this is called the twirling map. Okay, so why do we do the twirling operation? Well, one of the nice things about the twirling operation is that its output can be diagonalized in the so-called Bell basis. Okay, so here's a key point. The output of the twirling map is going to be diagonalizable in the Bell basis. Okay, so this is what I meant by kind of like a standard form, right? So you lose something in the twirling process because you're taking a pure state and you're mapping it to something mixed in general. But on the bright side, you get something that's now diagonalizable in the Bell basis. Okay, and in our particular case, we can write the following. We define F up here, right, where it was F. F was, our overlap with the singlet, right? We can, after this first step, we can write the expression for our state, right? So this is the state we started with that had overlap at least a half with the Bell state, with the singlet. And if I apply this twirling map phi to it, then, but like I said, you're going to be a mixture of the 4 Bell states now. So that's the singlet, that's the one we wanted, right? And you also get some weight on the other 3 Bell states. Remember, these are all 2-qubit states. Sorry, I'm too lazy to draw these Greek letters as proper capitals. Okay, and now what are the weights? So these form a north-normal basis over C2, right? So this is something in, technically in C4, right? So the weights now is F. So that overlap F is precisely going to be the overlap here. And then what's left is 1 minus F, but I have to divide it equally among the other 3 terms, it turns out. So I get 1 minus F over 3 plus 1 minus F over 3 plus 1 minus F over 3. Okay, so this ensures that when I add up all the coefficients in this mixture, right, this is a mixture, it's not a pure state, they sum to 1. So a trace condition is satisfied. Okay, and this is, again, just for clarity, this was for the Bell basis, which we've already defined in a previous class. Psi minus, psi plus, phi plus, phi minus. Okay, so that puts us into a nice form when we do this twirling. And now, of course, the point is that now I know a lot about the structure of my state, right? Regardless of what state I started out with, notice that I always end up with a state which looks like this after I twirl, in such a way that, as long as F was strictly larger than a half, now I know that the majority of the weight on my state is going to be here, right? This is the target state, and these guys have some smaller amount of weight. Okay, each of them. Okay, now what I really want to do is C naught, but before I do that, I'm just going to quickly switch local bases, right? So what I'm going to do is I'm just going to apply a local Pauli y basically to Alice's half, because as I mentioned earlier, right, if you want to switch between the Bell states, right, if you want to go between the singlet, where did that go? Distillation protocol. Yeah, here, this thing here, right? If I want to switch between the singlet and like the phi plus, all I have to do is apply a Pauli y locally, okay? And in particular, you know, I want to do a C naught, which will have the desired action on phi plus in the state I currently have. So I need to kind of switch bases using a local y. That's kind of the intuition. So now we're just going to apply a local y. Long story short, okay? So this was the output of the twirling map, right? Okay, so now here's step 2. Convert from psi minus to phi plus. Alice, so only on one side, Alice applies a Pauli y to her half, right? You can only do it on her half of each state. Okay, so she gets 2 copies of the following state, therefore this thing should look very, very similar to what we had up here, right? This was what they had previously. But now after the Pauli y is applied, then they'll have 2 copies of this state. Again, I'm going to have psi minus. Let me just write out the Bell states again. Psi plus. We're just going to end up moving the weights around. Phi plus, and phi minus, Okay? And so before, you know, the largest weight was here, right? And instead I'm going to put it on, instead of being on the singlet now, I'm going to end up putting it on this state, right? The phi plus. And that's because the C naught I'm about to do in the next step, you know, has the right behavior on this phi plus state. And then everything else just gets moved around. Okay, so and in particular, the second and the fourth terms just don't change at all. Okay, so all we did is we just, for clarity, we just swapped these guys around, right? Here versus this. Okay, and then you can compare. All right, so that's all the tensor y did. Okay, now step 3, and by the way, I'm going to write down all the steps, then we will try and make some sense of it. Again, it's a bit cryptic. I think in general, distillation protocols, at least for me, are a bit hard to decipher. Like, sure, you can run through the math, but it's one thing to run through the math and another thing to really see what's happening in some sense or why it works, okay? Intuitively, of course, what's really happening here is that there's got to be some notion of post-selection happening, right? So meaning that you're going to be doing some sort of local maps, which you know cannot increase entanglement. And so you have to do some sort of measurement, and with some small probability this thing is going to succeed. And when it does succeed, you can identify that it succeeded, because you can pick up the phone and call each other and see like, oh, Alice, what did you get? What did I get as Bob, right? And then you can compare. And if you get the right sequence of outcomes or a combination of outcomes, then you can project onto some more entangled state, right? But okay, we'll get there in a second. That's step 4, actually. So step 3 is the following. Apply C naught gates. Okay. And so let me just be clear that up until now, you know, everything was in tensor product, right? We had this thing. And then, you know, we had sigma A1, B1, sigma A2, B2, right? That's what our state has looked like up to this point. And now the C naught gate, what's it going to do? Now we're going to entangle these 2 copies. Okay, so we're going to do a C naught like this on Alice's side. Okay, and a C naught like this on Bob's side. So this is Bob, this is Alice. So this is going to have the effect now of entangling, you know, these 2 copies of the state, right? Before they were a product, they won't be product anymore at this point. So I'm going to try and delete that if my computer will cooperate. Okay. Okay, so just in words, the same story that I just said. I'm not sure why, but my computer always lags in the second half. Oops, no, let's not do that. Okay. Okay, so Alice applies C naught with A1 as control, B1 as target. Okay, and Bob does the same thing, of course. It's just that now he's dealing with, sorry, this is A2 here. No? Okay, so it's just a matter of doing it locally. Good, so now they've entangled their two systems, and now they're going to measure. Now, I have a 4-qubit system here, right? And if they were to measure both qubits on their side, you know, we would, generally speaking, not be too happy, because then we're collapsing everything down, right? So they're only going to, well, let me make sure I do this right. Yeah, they're each going to measure half of their qubits. So in particular, they're going to measure the second copy. So now they'll measure, Alice will measure this one, Bob will measure this one, right? And then they'll compare their answers. And if they get answers they like, then that means that this first copy will have been projected down onto something that's more entangled. Okay, that's the idea of this. Okay, so let me just write this down. Step 4, local measurements. And this is what I meant by post-selection, where you do a measurement, and if you get the outcome you like, you continue. Otherwise, you blow up your lab and just decide that you don't like science anymore. Okay, so post-selection means that you select on the output you would like to have, if you will. Okay. Okay. So Alice and Bob each measure locally. Okay, obviously that's all they're allowed to do. A2 and B2. And this just in the standard basis. Obtaining just a pair of bits, 0, 1, respectively. Okay, so A refers to what Alice got. B refers to what Bob got, right? So they measure the second copy, and then when Alice measures her side, she gets a single bit A as the outcome. They're just measuring the standard basis, right? And Bob does the same thing on his side. Okay. And now, if A equals to B, then life is good. So they keep the composite system on the first system, copy now. So this guy over here, they keep this one around. So they keep sigma A1 B1 prime, okay, a prime because it's been projected down. Okay. And if A is not equal to B, they throw out everything, the experiment, and say start again. Okay, so this is the part where the post-selection is taking place. Okay, so if they don't get the outcome they want, they throw a big temper tantrum and they just decide, you know, we're not doing this anymore. Where is, there, good. Okay, so that's the local measurement, and at this point you've already got kind of, assuming the post-selection worked, you've already got a more entangled state in your possession in that first copy, and then you convert back, right? We did a change of basis, we did a local Y operation, we just need to undo that. So that's kind of superficial at this point. Convert back from psi minus, sorry, phi plus we said, to psi minus. Okay, Alice applies y to her half of this joint state they have now. Sigma prime, sorry, it's not a ket, sigma prime A1, B1. Okay. So if it wasn't clear, just a quick clarification, right? In step 4 here, they're comparing their two answers in the experiment, right? So here's where you're using your classical communication. You're picking up the phone again and talking to each other. Okay. Okay, so so that's the basic protocol, right? So it's you first twirl so that everything now diagonalizes in the bell basis, right? Then you do a local basis change, which is kind of superficial, if you will. And then you do a C0 gate, right, to do the entangling between the two copies. You locally measure the second copy. That projects the first copy onto something nice. And then you compare your local measurement answers. If they're both the same, then you post-select. You say, okay, yeah, that was the outcome I wanted, and I know that the first copy's been projected onto something nice. Otherwise, you get different answers. Then you know the joint state was not projected onto what you wanted, so you just throw it all out and you start again. Okay, now of course that's rather cryptic, right? Let's try and do a bit of a concrete example to try and make some sense of this, right? And the analysis is a bit cumbersome, so I'm not going to go through the full thing, but I'll try and give you a sense of how this is supposed to go. So let's do a concrete example. Okay, and to be clear, so these distillation protocols like this one it's rather simple, but the ideas behind it are slightly more advanced. You may or may not normally put this into an intro course. So the point here is to show you a bit of a blend of kind of simpler things like the entanglement entropy and then slightly more complicated things like distillation. Okay, so let's suppose Alice sends half of the singlet, psi minus, to Bob. Okay, so she prepares the singlet perfectly on her end, and she sends half of it to Bob. But along the way, there's some error or some noise in the communication channel. Okay. So the communication channel has noise, right? And let's just assume the type of noise it does is it injects a copy of the maximally mixed state. So it just injects some random noise into your signal, basically, okay? So then, the state they have after Alice shares her half of the singlet, the joint state they have with the noise injected looks like this, right? It's here's your singlet, right? But they don't just have the singlet, right? They have some of the identity now, some random noise that came in from the channel. And let's just assume for now that, this was done in a half-half ratio. Okay, just to keep it simple. So suppose that this is their joint mixed state now. And now remember that the identity map or the identity matrix can be diagonalized in any basis, right? And in particular, since this is a 2-qubit identity, it can be diagonalized in the Bell basis. So if I do that, I could rewrite this entire expression like this. Okay, so I'm going to write down the 4 Bell states. No, it's psi plus, psi plus. Okay, and this will look slightly different than before because now I have some. Well, okay, sorry, I shouldn't say that. I know exactly what the value of f is here, right? Because I know exactly I started with the singlet. So originally f was 1. Then I injected some identity in there, and so now f is smaller than 1, right? In fact, it's 3/4, right? That was the coefficient in front of the singlet. And the other ones should all be the same. They're 1/12. Okay. So by the way, there's a special name we give to this channel, the one that injects noise. This is something called a depolarizing channel. Again, I don't want this to be just an information theory course because it's an intro course to QC, so it's probably better to keep things a bit more broader, so I won't get more into details about things like channels. But, if you're wondering what that thing is called, if people actually study it, the answer is yes, they study it. It's called the depolarizing channel. Okay, so let's see how each of the steps of the protocol now applies to this shared noisy state rho AB. Okay. Now, the first step, none of these I'm going to do in any serious detail, right? I'm just going to kind of sketch the idea. The first step, remember, the goal was to do this twirling, right? And when you do the twirling, what it does is it takes your input state, no matter what it is, and it makes it something that's decomposable in the Bell basis, right? Where the mixture depends on your fidelity with the singlet, right? And now, of course, in our particular example here, I mean, I'm already diagonalizable in the Bell basis, right? Just by definition, right? I was a Bell state, and then I injected the identity, which is diagonalizable in the Bell basis, right? And so intuitively, we would hope, at least, that the twirling operation should not mess anything up now. And indeed, you know, the first step we can, if you do the math, you'll see that the twirling operation actually leaves your state invariant. Okay. So this is part of the exercise. You know, I'm not going to go through all the steps, but, you know, basically you can show that, you know, let's suppose you chose Z as your local Pauli operator. What it will do is it just swaps between the Bell states phi plus and psi minus and vice versa. Is that right? Oh yeah, okay, sorry. It's a square root of Z. Okay. And you can say the same thing for root x, or an analogous thing, I should say. It maps phi plus to, oh, sorry, this is not right. This is phi minus, sorry. I knew it, something was funny, right? Good. To psi minus, okay. Sorry, psi plus. Okay, and square root y, tensor y. It maps basically phi minus to phi plus. Okay, and vice versa. Okay, so it just swaps back and forth between those states. Okay, and you know, when you combine these identities, essentially you should get that in this particular case, because our state is already diagonalizable in the Bell basis, twirling leaves our state rho AB invariant. Okay. So for example, if I look at phi plus and phi minus, right, what does this thing do? It just kind of swaps the state of these two, right? So, you know, the states, my state won't change under the action of this twirling map, basically. Okay. And you'll notice how none of these affect the phi minus state in this particular case, yeah, because I'm already in the Bell basis. Okay, so they're just kind of swapping between these three guys over here. Okay, by the way, so a quick way to check if using a trick, right? How do I know this, right? How do I know that? Let's just quickly do this one. Why is it true that square root z times tensor square root z on phi plus? You know, how do I evaluate this, right? I don't want to take square roots of anything, right? Blah, blah, blah. So remember from last class, this was very, this nice trick from non-local games, from the analysis of it, right? From the end of that lecture, we saw that if I had a tensor identity on a Bell state, right, I could always move that operator to the other side, but put a transpose on it. Okay? Only if this is a Bell state, right? 0, 0 plus 1, 1, right? I'm not sure off the top of my head if it holds for all of them, but it certainly holds for the standard Bell state, 0, 0 plus 1, 1. Yeah. So in particular here, you could see here that what is this equal to if I just apply this identity, right? You're just going to get that its identity, tensor square root z transpose, right? Tensor times square root z, right? Times phi plus. Okay, and square root z is still diagonal, right? Because the eigenvalue is sitting on the diagonal. You take the square root. So it's really just square root z transpose is square root z. Okay, so this is nothing other than I have square root z squared, which is just z by definition, phi plus. And if you think about it, if I apply a z operator to phi plus, remember what was this? This is nothing other than 0, 0 plus 1, 1. Right, okay, this is a proportional, right? I'm not writing my constants now. And that is equal to just 0, 0 minus 1, 1, right? and this is proportional to phi minus by definition. Okay. So even though there are these funny square roots here, in actuality, I mean, you can just move one guy over to the other side. Okay, good. So I hope that convinces you that at least in step 1, because the state we have is already diagonalizable on the Bell basis, the twirling operation really ends up doing nothing. So that's step 1, the twirling operation, which is usually non-trivial, but in this particular example, it turns out to be easy to analyze. It does nothing. So now for step 2. Step 2 is just a local change of basis, so there's nothing difficult about this. So I'm just going to leave it as an exercise, show that applying YA tensor identity on B yields, okay, so this is, sorry, it's clear that it's step 2, I don't need to write it again. And remember, all this will do is it'll swap around 2 of the Bell states, basically, right? So I get a half times the singlet plus a half times psi plus plus 3/4 phi plus 12 phi minus. Okay. So it's just it should just be moving these weights around, right? The weight used to be on the singlet, the 3/4, and now it's on the phi plus state, right? Just like before. So there's your 3/4 now. Okay, now steps 3 and 4. Step 3 is where we do the C0 gate, and step 4 is where we measure. Those are unfortunately a bit messier, right? I mean, so it's not difficult to analyze them. It's just that, you know, you're gonna have to write out a lot of terms, right? Because I have 2 states now living over 2 qubits each. So I have a total of 4 qubits, right? And so the number of states I have to write down to keep track of this is 16, basically, if I expand out the tensor product. So, you know, that's just very cumbersome. So let's not do all of that, right? Let's just do, let's just analyze one term in that entire computation, okay, for brevity. Okay, so let's analyze, so this is step 3. So let's analyze one term in the computation or the expression for brevity. Okay, so before step 3, right, Alice and Bob share a tensor product state, right? So they share sigma A1 B1 tensor sigma A2 B2. Okay, so that was this thing where they had 2 copies that were in tensor product, right? So there's nothing connecting these ways yet. Okay, and now of course they want to do their C0s now, and the C0 is going to entangle them, right? So remember, the C0 will come like this, right? On Alice's side, and the other C0 will be on Bob's side like this. Okay, and so they will become entangled. Okay, now if I want to, now of course, each of these guys, right, by definition, because we did the twirling operation, each of these guys is written like this, right? Right, so we have 2 copies of this guy, and now I have this guy tensored with itself on the left and the right. In order to analyze the action of the C0, I have to take the tensor product of this with itself. So I'm going to have 16 terms, and then I'm going to have to analyze the C0 on each of those 16 terms. Mess, right? So let's not do all of that. Let's just pick out one term in that expansion of 16 terms and, you know, analyze just that to give you a sense of how it goes. Okay. So the expansion in the Pauli basis, right, and by that I'm referring to this thing, right, has 16 terms. So let's focus on one. Okay, so when I expand out sigma A1 B1 tensor sigma A2 B2 in terms of these expressions, one of the terms I'll get will be phi plus tensor phi plus, right? I'll get that twice. So let's just focus our attention on this one. just to get a sense of how, if you were to do the full analysis, how it should go. So here's phi plus, tensor phi plus, phi plus. Okay. And so how does this work now? Any data? Okay. So let's just focus on this term in the expansion. Okay, and I'm going to do a C naught, right? So how does a C naught act on this? So this is an exercise in the notes. So show that if you apply C naught, and remember I'm doing two C naughts, right? I'm doing one on Alice's side and one on Bob's side, right? So show that if you do C naught from A1 as control to A2 as target, tensor C naught, B1 is control, B2 is target, and you apply it to this joint state, right? Phi plus A1, B1, phi plus on A2, B2. Okay, so this is just for the term that corresponds to this guy over here, right? So the claim is that if you work it out, and I'll let you do that on your own as an exercise so we don't get too sidetracked here in details, this equals to the following. Okay, so A1, A2, the order is important here, B1, B2. Okay. So the point here is that, I've got a mixture of 16 terms, right? And when I apply the C naughts to this term in the one of the 16 terms in the mixture as an example, right? This is just a projector, it's just a pure state, right? So that's why this is a pure state down here, right? When you do this analysis, you'll see that this is what you get on the right side. And so notice the split here, the first halves are on Alice's side, the second halves are on Bob's side. Okay, so that's this split A1, A2, B1, B2. Okay, and now now we look at this thing, right? And we say, okay, remember what we said is that after they do these C naughts in step 4, right? So this is basically, for clarity, this is after step 3. And this is, again, not for the full expression, this is just for this one term, right? Like, we're just looking at this one term out of 16 terms in the expansion here. If they were to just, this is a mixture, right? So I can analyze each of these guys independently, right? Because of linearity. And so if they measure, now they're going to measure, remember, A2 and B2, right? That's step 4. If they measure A2, B2, right? What is that? That's, we're looking at this and this, right? That's what they measure. Okay. So if they measure, and remember, what they do is they check, do they get the same bit or different bits, right? So if Alice and Bob measure and they get 0, 0, for example, they know that the first subsystem collapses onto 0, 0 as well. And the other case where they get matching bits is going to be if they got 1, 1, right? And then they know that the first subsystem collapsed to 1, 1, right? You'll notice that the other two terms in the superposition, like here, if they got mismatching bits, so Alice measured 0, Bob measured 1 on the second copy, they mismatched. This is when they abort the protocol, right? Because then their bits on the first system, those would have also mismatched, okay? The same argument for this one. So what is the post-selection doing for us? What does it mean to post-select on when they get like bits? Then these two terms are basically dying off. And it's this term and this term that stick around, right? So it ends up being, you end up projecting the first copy onto something that looks like a Bell state, okay? So, in particular, in this case, it looks just like a Bell state, yeah? So after step 4, if A equals to B, right, they project the post-measurement state on A1, B1 onto this thing, right? They get something proportional to, right? 0, 0 plus 1, 1. Okay? And again, the 0, 0 is coming from here. Here's your 0 and your 0, and here's your 1 and your 1. Right? This is A1 and B1. Okay? Okay, so that's kind of the intuition here, right? I mean, that somehow they do these C0s, and when they do the measurement and they post-select, then what happens is that they end up entangling that first copy together in a stronger fashion. Okay, that's at least the intuition. Of course, this example is not exactly perfect because, in this expression here, I mean, these guys were already Bell states across A1, B1, right? But this is just supposed to give you a sense of, how the computation is going. Okay. Okay, and finally, the last step is just to change your basis, so I'm not going to look at that. What does this buy us? Okay, so, we did the twirling, right? Then we did a change of basis, and then we did C0s, and we measured and conditioned on the outcome. We post-selected. We kept the first copy of the state around, right? And so the question is, what is this doing for us, right? And again, this is a tedious analysis, so I'm not going to go through it all, right? But the idea is that every time I run those 4 steps, okay, with probability at least a quarter, what one can show is with probably at least a quarter, this protocol, one round of this protocol, if you will, so it maps the input state. So you started with 2 copies of this thing. Okay. So to be clear, the statement I'm making now is not for our specific input that we considered, right? This is just for the general distillation protocol. Okay, and it maps that to an output state. Sigma prime A1, B1. So that if I define f of rho to be, just for brevity, because I don't want to have to keep writing this down, right? So this was the fidelity of our starting state was f of, well, whatever rho I put down here, that's going to be the argument here, right? Your overlap with the singlet. Okay, so the fidelity of the output of this protocol, here's sigma prime. What is that equal to? Well, it's the fidelity of the input. Okay, so here I have rho on the bottom, so that's the original state we started with, whatever that was, plus 1 over 9, 1 minus the fidelity of rho squared. So it's kind of a nasty expression, so just bear with me for a sec. I'll just write the whole thing out. F of rho times 1 minus f of rho plus 5 over 9, 1 minus f of rho squared. Okay, so you get this nasty expression. You can work it out. This is what you'll get, that if you run the protocol once and the post selection should succeed with it probably at least a quarter, right? Then you'll get some valid output state, sigma prime, and its fidelity will scale like whatever this function is, right? So we started with some input value of f rho, right? And so you can plug it in and you could evaluate what this comes out to. And the key point here is that if you started with your original fidelity being strictly larger than half, then you can show that this new state you got has strictly larger fidelity. Okay. Okay, so that's basically the crux of it, right? So every time you successfully run this protocol, you increase your overlap strictly with the singlet. Okay, and then you could repeat this over and over again, right? So imagine you have many copies of this thing, and of your input state, and then you pair them up and you run this protocol, and you slowly kind of distill down to a very small number of copies of something very close to the singlet. Okay. So again, so just some, so that's really all I want to say for this lecture, but let me just close with some remarks about this distillation, right? Again, distillation is highly non-trivial. I mean, at least to me, it all looks very cryptic, like no matter how many times I look at it. Ultimately, what's happening here is post-selection, right? Because local operations and classical communication cannot deterministically create or increase entanglement. So the only way you can do it is that you have to have some sort of measurement that succeeds with small probability, in this case like a quarter, right, that projects you down onto some desired state. And once that actually works, the measurement works, you get the outcome you want, you can post-select on that. You can say, aha, I got the outcome I wanted, I'm keeping my state. And then then you can kind of recurse this protocol. Okay, but post-selection is key, because otherwise you cannot increase entanglement under, on average, you cannot increase the amount of entanglement even under LLCC. Okay. Just some final comments about what kind of states are distillable. Okay, so this is just on distillability. This is actually not in the notes, but let me just make a quick comment. And by the way, typically, as far as I know, these, distillability is not really, and we don't care what is the probability of success in some sense. We're just asking, is the state distillable or not, right? In other words, if I take an infinite, essentially as large of a, if I want to get within kind of any overlap with the singlet, is there some sufficiently large number of copies of my input state I can take in order to do this distillation into, that good fidelity with the singlet that I want, right? That's really what we're asking. Nobody cares about what are the odds of this thing actually succeeding, okay? That's not the question that's being asked here. Okay, so in particular, let me mention that separable states, or including product states, are not distillable. Okay, so if you have no entanglement, like, sorry, you're out of luck, right? On 2 qubits, all entangled states, mixed or not, are distillable. Okay, and I believe the way the proof of that goes is there's another protocol you first kind of plug or prepend onto what we did today, the recurrence protocol. There's another protocol you do first to get your fidelity up to at least a half with the singlet, and then you can run this recurrence protocol. Okay, but 2 qubits is a very, very, very special case. For 3 plus, sorry, let me not say it. For 2 qubits and up, there exist entangled states. So they're entangled that cannot be distilled. Cannot be distilled. Which is kind of surprising, right? I mean, oops. So you have states which are entangled, but their entanglement is kind of not accessible, if you will. I don't know why I want to leave this. Okay. Cannot be distilled. Fine. Okay, and the name we give to these states are called bound entangled states. Okay, so these are bipartite states where no matter, they're entangled, but no matter how many copies you take of them, you can never get arbitrarily close to a singlet by doing any distillation protocol. Okay. Okay, so that's all I wanted to say for this lecture. Just as a recap, we did entropy and entanglement distillation, right? So we covered the entropy function, which is a very central concept to information theory. Okay, very, very important. We could have spent multiple lectures just on that alone. We showed how that generalizes to von Neumann entropy by going through the framework of operator functions, okay, where we apply a function, a real valued function, to the eigenvalues of an operator. Okay, and then we showed that once you have the von Neumann entropy in your at your disposal, you can then go ahead and quantify how entangled a pure quantum state is, a pure bipartite quantum state. Okay, and that technique completely breaks down if your states are mixed or multi-party. And finally, we did entanglement distillation, which is that, if I actually want to, if I have a source that's producing noisy entangled pairs across distributed parties, and I want to kind of boost this up to Bell pairs so I could do something like teleportation, can I at least in theory do it using local operations and classical communication? And that was where we showed the answer is yes in certain settings. We gave a 2-qubit mixed state protocol called the Recurrence Protocol. And that was this process of entanglement distillation. Okay. So that's it for this lecture. I hope you guys have a good week. As usual, any questions are welcome on the chat board on Panda. And yeah, have a good one, guys.